In this video, we're going to have an overview of the analysis techniques used to design steel structures according to the New Zealand design standard NZS 3404. When we look at these analysis techniques, it's going to be a bit of understanding, well, how do we get the demands which we're going to use to design our steel building, as well as what are some of the underlying assumptions there. And so when we start with this, we're looking, sort of broadly at what are the different types of analysis methods we can use. And 344 allows you to use one of three methods. You can do an elastic design. You can do an elastic design where you then redistribute moment and shear once it's reached a critical point, or you could look at a plastic analysis. So just briefly, we'll look at a propped cantilever as an example for what are these three different methods? The elastic design is what you would be familiar with if you've gone through statics or indeterminate analysis, where you're just purely getting out what the moment and shear distribution would be based upon a static analysis. In the middle here, we're using a elastic distribution of forces, but then you're allowing for some redistribution. What that means is that once you reach yield, or your plastic moment capacity at some point in the structure, in reality, because that plastic moment is only going to allow a certain amount of force to be generated at that point, if you keep putting on more load onto the element, well, that load's going to go to other parts, it's going to redistribute around the element. And so there's an analysis technique which allows you to take advantage of that. And what that means is you can get away with a slightly smaller element that you couldn't if you just did a purely elastic design. This is really important for when you do seismic design and you're looking at very large forces, and say you're designing a moment resisting frame. Well, if you were to do a purely elastic distribution on that, then you would end up with very, very large elements. While if you do some redistribution and you account for that, you can understand that you're going to get some yielding in that frame, and that if you design and detail that accordingly so that it has good deformation capacity and it's nice and robust during the earthquake, well, then you can actually scale down the size of your elements and just understand that as you yield at one point, it's going to redistribute around the rest of the element. And the final method, which is explicitly talked about in 3404, is a plastic collapse mechanism. Again, this is a gravity example which is shown here on screen, but this is very useful for seismic design. And really what you're looking at is collapse mechanism. So what's shown here is the three collinear pins, so three pins in a row. That's unstable, and you're looking at the development of plastic hinges, so plastic moment at locations and in a distribution such that your structure will no longer be stable. So that's the overview of the three, which are explicitly stated in 3404. For this video series, we're going to look only at elastic distribution and sort of what's included within that. So if we move on and we talk about elastic distribution, what does that mean sort of more explicitly? And really, when we're doing an individual member analysis, we're doing what's called a first order analysis. And that sounds fancy, but a first order analysis, if you've done statics before, is exactly what you've been doing. This is our classic static analysis where we're using forces and moments and making sure they're in equilibrium, and that's what our distribution is. It's also assuming that plane sections remain planed, and so moment curvature relationships hold true. And where does it allow you to use this? Well, because moment curvature is assumed to be hold true, you can use it during the serviceability limit state. And remember, at the serviceability limit state, these are the loads and demands which are on the structure day in and day out. So this is primarily looking at things like deflections, vibrations. And so if we look at what the demands on the cross-section would be, so say we have this I-beam and it's right at that point of where the load is applied, well, for the serviceability limit state, we're assuming that the entire section stays elastic. So there's no point along the depth of that section in which the bending stresses exceed yield. And so that also means that our moment demand, m star, is going to be less than our plastic moment. And we can also use this for the ultimate limit state. And remember, our ultimate limit state is what we're designing for. This is sort of not necessarily our worst case scenario, but this is really all we want to make sure that from a probabilistically large load, that our structure is still going to be able to withhold, and withstand that with limited damage to it. And so that limited damage in which we designed for steel is the development of the full plastic moment. And what that means is that while at serviceability limit state, the entire depth of the section is elastic, at the ultimate limit state, the entire depth of the section has developed plasticity. So the stress, the bending stress is going to be equal to the yield stress over the entire depth. And the little note where it says, can reach where appropriate, the only caveats to that, and we will see this as we go through the videos, subsequent videos, is that if you might not be able to reach your plastic moment if some element within your section buckles prior to that. So that might be the entire member, buckles and global buckling. That might be a flange or a web, buckles under local buckling, some plate buckling, but that we'll talk about more. And then the last thing that you really have to be cognizant of when you're doing an elastic analysis is you have to account for second order effects, or what are called p-delta effects. Now, let's have a quick look at how to do that. So the first thing that you have to do is you got to get your first order moments. So I have a little example here. So say we've got a simple one-story, one-bay frame with a point load on it. Well, in order to get our first order moments, we would of course draw our free body diagram, do our statics, understand what our bending moment distribution is, and then plot that up. So that's our first order moments, and as I said, that's just purely what would be coming out of whatever analytical method you'd be using. So either some hand method of indeterminate analysis, such as moment distribution, or even if you're getting this out of a software package which only is doing sort of your first order shear and bending moment distribution. Once you have that, then you need to account for these p-delta. So what do I mean by p-delta? Well, if you have a member which is in compression, well, we know that things which are in compression have a tendency to want to buckle. And this tendency to buckle is sort of key to try to design around for structural steel. Now, that buckling, so say we have this applied axial load P. Well, as things buckle, they deform away from their original center line. And so this cantilever, you would have P, and it would be deforming by some distance delta. And if we know that a force times a distance is going to be a moment, well, we get this second order moment of magnitude P times delta. And the way that we deal with this for an elastic analysis in 3404 is we go, well, let's just take our first order moments and simply scale them up by a factor, which is going to be proportional to P delta. And this works fairly well for what are termed regular structures, or elements which are have sort of equal base spacing. They don't have really weird loading on them, and they're also not overly slender. And when you have, and that covers actually a lot of structures out there, when you do have those more atypical elements, well, then you need to do an explicit second order analysis. And that's out of scope for what we're learning here, and that's because it is a very complicated, it's a nonlinear analysis, and there's methods which are also discussed in 3404, particularly in Appendix E. So that's our overview of how we, the analysis method that we're going to use. Let's dig into a couple of details there. So one of them is the span length of the element. So we're saying we're going to do some statics on it. Well, one thing that we need to know is how long are our beams, how long are our columns. So for beams, 3404 says you should take the center to center of each support, and that's the length of your beam. So we'll bring an example up here for when you've got simple connections. And remember, simple connections are effectively pinned because the webs are the only thing which are connected, the flanges are not. And that's what I've got drawn up here. So if we're to go center to center of the supports, well, the supports of this beam are the two beams which are running in and out of the screen at you. And so we'd go to the center line of those. And then in order to do our analysis, well, the length of this beam which we would be analyzing is going to be center to center of the ports. And because they're pin connections, we can model this beam as simply supported. So that should be pretty straightforward. Now, where we get a slight complication is when we go to rigid and semi-rigid connections, and we do the same rule for both. And this is in the commentary of 3404. It says when you have these type of connections, you're allowed to reduce the moment demand on the beam or on the column to the face of the element it's connected to. So we'll start looking at beams. And so how do we do this? Well, let's run through a sort of graphic example. So first thing we want to do is, do our analysis based upon the center line distances of the member. So just like all of the other examples I've shown you so far, we would get our shears and our bending moment diagrams, assuming that the length of the beam is going from center line to center line of the supports. And so you'd end up with a moment distribution, something like this, where you would end it at the column center line. Now, granted, for when you get to designing some beams with large loads, particularly from seismic, but also for large gravity loads, the center line becomes really, the moment there becomes really large. However, physically that doesn't make a lot of sense because that joint is, we're going to design it and fabricate it up, so it's essentially a rigid box. It's not deforming like a beam. And so it doesn't make sense to design it for bending and moments which would occur sort of at a beam face. So what we do is we cut this off at the column faces. And essentially, so I've got a small equation up there where you take, you find your center line moment demand at the columns, and then you subtract out the moment, which is just simply the shear in the beam multiplied by the depth of the column divided by 2. Now, this is a nice handy little equation. However, I encourage you not to memorize it because it's way easier to simply think about what's going on from a statics and a shear and bending moment demand. So if you recall that the area under a shear diagram is simply the value of the moment at that point, well, that's all we're doing here is we know that we've got the shear between the column face and the column center line. Well, we're just simply taking that area under the shear force diagram, and so that's equivalent to our moment at the column face, and we're subtracting that out. And we can do a similar thing if we're looking at columns, where, again, we start, say we've got this simple frame which is getting pushed over. We start with the center line of the elements. We get our first order moments, which are based upon the center line. And then we reduce them down to both the column and the beam face, simply using that reduction based upon the shear force and the depth of the beam for the columns and the depth of the column for the beams, and both of those divided by 2. So this should, take some time if when you're looking at this and you're confused. It should hopefully, after a little bit of pondering, you should see that it's really just a geometric. It's a similar for this one. It's just simply a similar triangles. If you've got say a quadratic distribution of moment, well, in that case, you're really just looking at that, taking the area of the shear force in that sort of half the column depth, and you're subtracting that out to get the value of the moment there at the column face. The final thing which I want to go over is around the approximate analysis of frames. So steel buildings have a lot of frames, both moment resisting frames and braced frames, and often these buildings which we design are very regular in format. And so a regular building is one in which you've got more or less equal base spacing, more or less equal loading. You don't have really weird openings or offsets. It's regular. And so in that case, the standard allows you to analyze each part of the building. Say you have a series of parallel frames, you can analyze those independently. You don't have to account for the interaction between them. And you can do that in both, primary directions of the building. The caveat for this is when you're doing seismic or wind design, you do have to look at the whole building. So this approximate analysis really only works for gravity loading. And the reason that for seismic and wind loading we have to consider overall structure, that's because the floor diaphragms and the movement of the building is really important for its overall stability and performance. And you really do need to look at the building as a system. But for the scope of what we want to look at, we can just look at these sort of parallel frames for our individual design. Now, for this approximate method, if you've got a multi-story building, it also allows you to essentially do a subassembly design, so that you can look at this from a sort of floor-by-floor level. And the advantage of that means that we can use some hand techniques relatively quickly. We could code them up in a spreadsheet, and that is really useful for us to get initial sizes of beams and columns, as well as to just do a reality check from our numerical analysis. And it's a really, really important skill to have, and particularly as a young engineer, before you really develop all those years of, sort of feeling of like, beam size should be about that, and you have sort of that inherent understanding. This is a really good sort of reality check tool. So I'll just run you through a quick example of how would we set this up. And we'll use the project which you're going to have in this class. So it's nominally a building which is has brace frames in one direction with 12 meter spans. And this is our secondary beams are all of the ones which are in magenta, so the columns are in blue. And those are simply connected, so they're nominally pin joints, so no connection between the flanges and subsequent and supporting members. In the perpendicular direction, where we have these 9 meter bays, it's a sway system, so these are moment resisting frames. The beams here in cyan are going to be rigidly connected, and that's what we're going to look at for our example, is how would we analyze this? Well, the first thing we can notice is the building looks very regular. It's a big square box. It's nothing really that complicated, so that means that we can use these simplified techniques, number one. And so because of that simplified technique, that means that we're allowed to analyze each of these frames sort of independently. So we can, all the parallel frames we can analyze separate. So that's what we'll do. So we'll take this slice through the building here, and this is sort of what a cross-section would look like, where you can see the columns there, a 3-story building, and primary beams running across the screen, and you can see the eyes where the secondary beams are coming out. Well, the way we would analyze this, because if we stop and think, this is a rigid frame. If we wanted to do this sort of, quote-unquote, the right way, well, we would apply all of our loads and we'd analyze it, and that's a lot of joints, and we could do moment distribution throughout the whole thing. But then that becomes really complicated. It sort of defeats the purpose of a simplified, approximate method in order to help us understand the structure, understand the demands on it, so that when we use more sophisticated tools like a numerical analysis package, we have some confidence that the output that we're getting from there is sensible, as well as being able to give ourselves a good handle on getting some preliminary sizes for this frame. So, because we don't want to analyze this as one big element, well, we can take advantage of a few things. So first, it's symmetrical. So, if we apply our loads to it, loading is symmetrical in this case. Oh, this is our axis of symmetry. That means we only have to analyze one side. And if you recall back from moment distribution, this is a method which is quite common with symmetrical structures. The second thing we're going to do, because it's a rigid frame and everything's regular and similar uniform loading on all bays, on all stories, that means we can break this out and design it sort of story by story. And so the general free body diagrams we would have for that is the top story. We would have sort of this element C, D, G. The middle story, we would have this T section, and the bottom story, of course, have another T section. And now we have 3 separate structures in which we can analyze. These are relatively simple structures if you're going to do moment distribution on them. They only take a few sort of lines of distributing moments and doing your carryover moments before you sort of converge on a solution. And so we would do that. So we'd run that through, and we would get our moment demands on each of these elements. And cool, that seems useful. But the astute among you will notice that, well, there seems to be some problem. We have two, joint Ds, two joint Cs, and two joint Bs between these three different structures. Which moment demand do we use at each of these nodes? Do we try to sum all of them up? Well, that doesn't seem to make a lot of sense. It seems like we're probably overloading the structure. And the best way I can give you some intuition as to why we're going to make the selections we're going to make is if you think back to how moment distribution method works. Essentially what it's doing is it's distributing around moment demands based upon the relative rotational stiffness of a joint. So, and that's where your carryover factors come in. So that's why at a fixed end joint, you always have a carryover 1/2. At a joint which is not fixed or not pinned, it's going to be dependent upon the stiffness of the elements framing in. So what we want to do is select the moment demands which most closely represent the real stiffness of the joints. And so I'll just circle them quickly. For the top structure, that means that's the demand that we want, because that's the moment demand from it framing in with two elements, so the column on the third floor and the roof beam coming in. For joint C, we want to use this middle one because, again, that's where those elements are coming in. And then for B and for A, we've got them circled there for much the same rationale. And so this can take a little bit of time. I know when students first look at this, it's a bit confusing, but again, always think about we're using these approximate methods, and so when we're going to apply them back to our structure and we're going to try to combine all of these in, essentially what we want to do is take the moment demands at each of these points that we've circled in, combine them back in, and then that draws our entire moment distribution for the structure. The other good way, in order to make sure that you have done your recombination correctly, is that at each joint your moment demand should sum up to 0, because that joint has to be in equilibrium. So, wrapping up, just a quick review over what we've gone over. We looked at our analysis techniques, and remember that we're going to focus on using an elastic analysis, and that's going to be much the same as what you've learned if you've gone through statics courses. But the big thing that's going to be different from that you've probably not seen before is we need to account for second order effects. So these are these P delta effects, the effects of deformation when an element is in compression and it wants to buckle. We also looked at the span length of members, and again by default we're going to go from centerline to centerline, and that's going to hold true particularly for pin connections, nominally pin connections, so these simple connections. But if we've got rigid or semi-rigid connections, we can reduce down that moment demand to just what's at the beam or column face. And then finally we looked at some approximate methods in which we can use on regular structures, and so that we can do some subassemblies of structures and sort of more simple analysis, and then recombine those back later in order to get a good approximate understanding of what the structure is going to do. So with that, thanks for watching.